a frantically ridiculous amount of work all the time. I do not know how he's so prolific. He's currently a postdoc at CMU with Thomas Stenholm, and got his PhD from UC Irvine with Pierre Balti. Yeah. Spent some time at DeepMind, where I assume, or maybe how your work with Mark Langto got started. Langto. I don't know how to say people's names. Anyways, we're really lucky to have you, and I'm excited to see the talk.
Yeah, thanks, Eugene. So this is kind of a tortured acronym, eschewing important sampling in games by computing a history value function to estimate regret, or ESCHER. And this is work that builds off of counterfactual regret minimization. So I'll kind of give like half the talk will be sort of a tutorial on CFR, and then we'll talk a bit about the new thing that Escher does on top of deep CFR to make it work. But before we get to that, just some background and some motivation. So a natural question that we're probably all interested in is, how do we make optimal sequential decisions in the presence of other decision makers? So if I'm a self-driving car, if there's no other cars on the road, then this problem's pretty much solved. I can just, go from point A to point B. But if there's other cars on the road, then this becomes a really tricky problem. So how do I take actions when there's other drivers? If I'm a robot in a warehouse with a bunch of other robots, maybe I want to coordinate all their actions simultaneously. So how do we do that? Maybe if I'm a platform, how do I mediate a bunch of buyers and sellers that are cooperating and competing on my platform? And the perspective that the deep multi-agent RL community takes is one that focuses a lot on scalability. So from deep reinforcement learning, we have that if we can specify maybe like a simulator and a reward function and just scale up with the amount of compute, then we can essentially solve any problem that we give it. So we have this natural way of scaling things up with reinforcement learning. And a lot of the deep multi-agent reinforcement learning literature takes this single agent RL and changes something about it to make it work for a multi-agent setting. So maybe in a cooperative setting, you'll take, say, independent PPO, and then make the value function be centralized so that all the agents get the partial information of the other agents. And then this works really well in practice, and it scales up really nicely. Maybe in a two-player zero-sum game or a two-team zero-sum game, like we have on the bottom here with OpenAI and Dota, you just take independent BPO, but then have it play in self-play. And this works really nicely in practice, scales up really nicely. But the downside of this sort of approach is that many of these types of multi-agent RL solutions might fail even in small games. So Sam was talking about this the other week, where if I take self-play policy gradients, for example, and have them play rock, paper, scissors, then they're just not going to converge. They're going to keep spiraling outward and outward, and not going to converge to a Nash equilibrium, even in average iterates, I might add. So the perspective that I like to take is what I call the game theoretical point of view. So if a lot of multi-agent RL focuses a lot on scaling, then game theory kind of focuses on the opposite, which is I want to focus on the smallest games I can think of and make sure that the algorithms that we come up with are guaranteed to work in these really small games. So the game theoretical approach says, let's define some game like this rock, paper, scissors game or some poker game on the bottom, and let's find and analyze the equilibria. So in particular, I'll focus on Nash equilibrium, which is a set of strategies for all players such that no player wants to deviate. So we would expect that if we're at a Nash equilibrium, then this is stable in the sense that learning agents or rational agents won't want to change their strategies. And in two-player zero-sum games, which is what I'm going to focus on in this talk, Nash equilibriums are a really great solution concept because it's, in a sense, minimax optimal. So I'm doing the best that I can, assuming that you're doing the worst that you can against me, which is a good assumption because your reward function is the exact opposite of mine. So if I play a Nash equilibrium in a large game like poker, for example, then I'm just going to be superhuman performance because no humans can play a Nash equilibrium. So I think that we want algorithms that kind of have both of these nice properties. We want algorithms that scale to large games, but also have nice game theoretical guarantees and work in small games and make sure that everything's based on these good fundamentals and good theory. So, So I want to focus on two-player zero-sum games, which is what I've been mainly working on. And the reason for this is really just because it's the simplest setting that we have right now. So once we start going to multiple players and general sum, then things become a lot more dicey. We don't really have good solution concepts. But in two-player zero-sum games, like I just mentioned, the Nash equilibrium really is a strong solution concept. So we kind of know what the objective is. And now we can focus more on the scaling part. So this is really where the deep reinforcement learning comes in. So what I'd like is to have general algorithms that are able to, just with a lot of training and self-play, arrive at an approximate Nash equilibrium in these really large two-player zero-sum games, but are game theoretical in the sense that they'll also work if run a tabular version of them on a normal form game or some small extensive form game as well. So I have Stratego here in the middle as this motivating example, which is something that I've been working on for a while, but I guess, with this recent paper that we just put out, we've gotten expert level on Stratego. So this is sort of becoming one of the things that we've already done, and now we're moving on to other games such as Dark Chess here on the right. But I'm not going to talk about the Stratego paper that much in this talk. So the landscape of what I call game theoretical multi-agent RL, mainly for two-player zero-sum games, I kind of view it as three main broad categories. So the first one is based on counterfactual regret minimization, which is what I'm going to be covering in this talk, so I won't go into the details here. The second category is on policy gradients. So back in 2018, there's this nice DeepMind paper that made this connection between just normal Q values in reinforcement learning and counterfactual values from CFR, which we'll get into the details of what those are, where you can essentially view one as being like a reach-weighted version of the other. So then some follow-up papers that have kind of explored similar veins, neural replicator dynamics, actor-critic hedge, and then recently this deep Nash paper that we talked about kind of combines neural replicator dynamics with this reward modification trick to get last iterate convergence in normal form games. So this is able to beat experts at Stratego. And then, of course, Sam had this great presentation on magnetic mirror descent a couple of weeks ago. So policy gradients are a really exciting approach. They're the closest to reinforcement learning that we have. So a big pro is that we can use a lot of the same tricks that we have from reinforcement learning directly and expect it to transfer over to better performance. And we can get last iterate convergence. But unfortunately, a lot of the results that we've seen so far require either careful tuning of step sizes or this reward modification. And I'm not convinced that the extensive form guarantees are actually as good as you might hope for, as something like a CFR-based method would have. But of course, CFR has methods based on CFR have their own downsides, which we'll get to. And then sort of this third approach is really the most different out of these three. So policy space response oracles. In this, you iteratively add best responses, which you can learn through reinforcement learning, deep reinforcement learning. So is this question about the policy gradients or the PSRO?
Oh, sorry. The question is about policy gradients methods.
Oh, yeah. So the question is like, what guarantees do we have for any of these policy gradient methods for extensive form games? There's really not much, to be honest. in my mind. Actor critic hedge is actually kind of decent, but again, it doesn't go all the way in like getting really rigorous theory, but it works really well in practice, or decently well in practice. So maybe there's some theory that maybe these methods as they are could have good theory, or maybe we need to tweak them a little bit. So this is something that I'm like actively working on right now. So if you're interested, we should definitely talk at some point. So for PSRO, it's really sort of this completely different approach where I'm not trying to minimize regret or come up one policy that does well at all these information sets, but instead I'm just trying to do this double oracle approach where I keep on adding best responses to my population, and then I mix over those in the way that I hope approximates a Nash equilibrium. So in particular, I want to highlight XDO, which came out last year, where the way that we mix over these policies, instead of just mixing at the root of the game, we mix over different policies at different information sets. So at every information set, I can mix over my population from scratch every time. And what's cool about this is that now this restricted game is essentially an extensive form restricted game. So we can bring in these other algorithms based on CFR, based on policy gradients, or even like NFSP or something like that. So any advances that we make on these other two categories should help with XDO. So they're really sort of complementary methods in that sense. Okay, so unfortunately, there's just going to be a lot of notation here. I try to keep things kind of similar to the reinforcement learning notation, but there's some differences. For example, I use utility instead of reward. So please don't hesitate to stop me as I go through this. But there's just a lot of notation that you need to kind of get to the point of understanding counterfactual regret minimization. So first, before we get to counterfactual regret minimization, let's think about regret minimization in normal form games. So the regret of an action, or really the regret, is going to compare to the best action in hindsight. So I'm going to say, well, sorry, first, let's say the setting. So the setting is I'm playing a repeated normal form game against some adversary. Okay, so think about like rock, paper, scissors, for example. And I look at all of the actions that my adversary took at time t=1 to time t, my current time. And I say, if I could only choose one action and play that same action at all time steps against this player, what would that best action be? And then what action did I actually take? And that difference is going to be my regret. So ideally, I would like an algorithm that converges to zero average regrets over time. And if the reason for that is if both players play no regret in a two-player zero-sum game, then the time average will converge to a Nash equilibrium. So these no regret algorithms, essentially all they do is just every time step, I'm just going to update my distribution, my current strategy or current policy, to sort of upweight the strategies that I wish I took, and to downweight the strategies that I regret that I took. So in this example, let's say we're playing this weighted rock, paper, scissors game, and I choose the middle action and the column player chooses the right action, and I get this reward -2. So the column player likes this because it's trying to minimize. So the next step, this no regret algorithm will put more mass on the action that was chosen and less mass on the other actions. And then the row strategy will put less mass on the action that was chosen. So this is the general concept of no regret and regret minimizing algorithms. So there's a whole class of algorithms that have this sort of property. We don't need to go into the details of them, but if you're curious, the counterfactual regret minimization uses one called regret matching. So we can talk about this later if you guys are interested in that. But just know that, so if I just run these two no regret algorithms in self-play, then I can get this approximate Nash equilibrium in the time average. Okay, so this is for normal form games, but if we care about sequential decision making, we're going to need to think about extensive form games. So extensive form games are sort of this general framework for thinking about sequential decision making when there could be incomplete information. So just think of like a poker game, for example. So I have some cards, you have some cards, and the history H is the ground truth state of the game. So this would be all the cards for both players, for example. But the information set S is kind of like an observation and partially observable reinforcement learning, where it's just what I observe as one player. And it's not just in this time step, but you can think of it as like the sequence of all observations I've seen so far. So you can think of this, we have this diagram where the information set S is sort of this collection of histories that are consistent with my observation. So like if we're playing one card poker and I get the queen, then my information set is like I see the queen, but the set of histories that we could both be in are all the cards where I have a queen and you have another card. Okay. So any questions so far on the distinction between history and information set? No. Okay. So the policy is the same thing as in reinforcement learning, but the thing to recognize is that this is a distribution that's conditioned on the information set. So when I'm acting in the game, I only have access to my information set. I don't actually know the true ground truth history of the game. So my policy just needs to condition on that. And the reach probability. So this is the joint probability of reaching a history H under policy pi. So policy pi is going to be the joint policy. And later on, we might specify like the reach probability of pi minus I. So that's going to be the joint probability of all the other players, including chance, of reaching that history state. So by joint probability, I mean, you just look at every decision node and multiply the individual probabilities on that path to get to that history. Okay, so last set of terminology. The terminal history Z it's just a history, but it's at the end of the game. So we're just going to denote it by Z. And the utility is the utility for player I. So UI of Z is that player's utility. So this is just the reward that they get. Okay, so this defines an extensive form game. And again, we like to find a Nash equilibrium of this game. So the idea with counterfactual regret minimization is that we want to minimize the regret. We want to run no regret algorithms on this extensive form game. And the way that we do that is there's a theorem that we can independently minimize the counterfactual regret at every information set. And the cumulative counterfactual regret over all information sets is going to give me an upper bound on the total regret I have in this game. So as long as every single one of those gets minimized independently, then I know that my regret is also going to get minimized. Okay, so some more notation here. So this, we're going to say that the value of a history H for player I under joint policy pi is just going to be the expected value if both players play from policy pi. Okay, so this is really similar to value and reinforcement learning, where it's just I'm going to look at all the terminal histories that are consistent with this history, look at the joint probability of going from this history to the terminal history as my weighting, and then look at the utility or the reward that I get in being in that history. Okay, so the counterfactual value at a information set S. So we're going to take our history value function here, this vi of H, which is defined above. And when we're in an information set S, we're going to look at all the histories that are within that information set and weight them by this particular reach probability of the opponent's policy, including chance of arriving at that history state, at that history H. Okay, so this is sort of an expected value in a weird sense over the histories in S, weighted by this opponent reach probability. So it's kind of this weird definition, weird formula, but it's just what you need when you do like sort of this backwards recursion to bound the total regret. Okay, so we're going to do the same thing that we did before, where we're going to define our total regret as going to be what's the best action that I could have taken in hindsight. But instead of this being the utility, like it was in normal form games, now this is going to be counterfactual value. So we're going to say the counterfactual regret at information set S with action I, with action A, is the difference between the counterfactual Q value and the counterfactual value. And sorry, I don't have the definition here, but the counterfactual Q value is the same thing as the counterfactual value, but conditioned on having taken action A. Okay, so any questions on CFR? I guess I'll do this one more bullet point and then we can stop for questions. Okay, so how does the CFR algorithm work? So again, what it's doing at a high level is it's computing counterfactual values and counterfactual regrets at every information set, and then running some no regret algorithm, but on the counterfactual values to minimize counterfactual regret. So the way the actual algorithm works, if I were to do this in a tabular CFR algorithm, is I'm going to traverse the entire game tree and go all the way to the end, and then get those utilities, then go all the way back, and then I'm going to use that. Then I can calculate the counterfactual values, and then update the policy via no regret at every information set. Okay, so I'll stop here and take questions on CFR. I know it's super fast to go through CFR, and it's kind of a confusing topic. So. Any questions? Okay. Okay, so Monte Carlo CFR, building on top of CFR, a lot of times traversing the entire game tree is too costly. So for example, it might be too large. I can't fit everything into memory. So instead, again, this is a tabular algorithm though. It's not a, okay. How do I calculate and update the best action at every time step? Yeah, good question. So at every time step, or really like at every information set, I have a policy, which is my current policy. And it's not, so it's not the best action. The best action is just like in my definition of regret. And my no regret algorithm is just minimizing regret. So this policy is just being updated via a no regret algorithm on the cumulative counterfactual regret. So for the regret calculation, so this, like, how would I get this? So this would be like, I have a discrete set of actions. Okay, so I have like, 5 different actions, and I can see which one of them has the highest regret. Just the same way as in here, I would calculate the maximum regret action as just by like, enumerating over all my actions, seeing what my utility would have been, and then comparing it and seeing which one has the best one. So does that make sense? Okay. But yeah, you don't actually ever do this like calculation of like finding a max over all the actions. This is really just for the analysis, where these no regret algorithms make sure that this quantity converges, like grows sublinearly. but the actual algorithms, all they do is keep track of cumulative counterfactual values. And then kind of like this example I have back here, I'll just, these no regret algorithms will just upweight and downweight different actions based on their cumulative counterfactual values. So you don't actually calculate this this term. Okay. So Monte Carlo CFR, often it's too costly to do full CFR. So instead, I'm going to just sample one trajectory. So I'm going to start from the root and sample all the way to the leaf node. And then I'm going to update the information sets along that trajectory. And the idea to get convergence and to get some theory for MCCFR is I'm going to include this important sampling term so that I remain unbiased. And the reason I want to be unbiased is that we have this nice theorem that says if I update information sets in an unbiased way, then with high probability, I'm going to converge to a Nash equilibrium if both players run this sort of algorithm. So if we look at this, this is sort of a VI hat. Sorry, this would really be like a VIC hat. So this is my estimator for counterfactual value for MCCFR. Now let's just go slowly through this. So I'm trying to estimate the counterfactual value, and I introduce here this random variable z, and the z is the terminal history that I actually sampled, and I'm going to view this as like a random variable that I get from my sampling distribution. So as I sample, I can view this as sampling terminal histories, like via this sampling procedure. And the estimator that I construct, so this should look really familiar. So the z of s, this notation just means the actual history that was encountered along the path to get to z. So I guess going back here. So if this is my z right here, then my z of this s will be this history right here. Okay. So it's just saying if I have this z and I'm looking at this s, this is the history that I got along that path. And there's only one of them. So this is really exactly the same thing as our definition of counterfactual value, except we don't have a summation here over all of the terminal histories z. We're only looking at the actual z that we got. Okay. So we're just saying it's my CFR estimator, but only on this this one path, essentially. And then I include this important sampling term here on the bottom, which is my reach probability of actually getting to that terminal history z. So you can see what happens is, like, the reason we do this is that the expected value, if I looked at the expected value of this estimator, then the probability of reaching all the z's is just going to be exactly this term. So it'll come out to be exactly equal to CFR, because my expected value of this term is really going to be equal to the value as well. So this MCCFR estimator is unbiased, and that's why we get these convergence results. Another way to look at it is that if you kind of rearrange some terms, this green part on the right is sort of the unbiased estimator of the history value. So it's kind of what I was mentioning earlier, is that this part on the right is to estimate the history value. And if we kind of break apart the terms from the important sampling term, this alone is sort of an unbiased estimator of the history value. And then this here is just sort of like this additional weighting term to make sure that I update all the information sets roughly equally. So that's another way to view MCCFR, and we'll come back to this really shortly. Okay, so deep CFR and DREAM, what we're going to do here is scale up to even larger games that MCCFR is too small for. So MCCFR was a tabular algorithm, but on like really large games like Stratego, Dark Chess, I'm not going to be able, like, the vast majority of all the information sets will be ones that I haven't encountered during training, so I need to generalize using neural networks. So what we do is we just build on top of MCCFR. So we use MCCFR to get trajectories and to get our estimator, and we're just going to add these estimates, these CFR counterfactual regret estimates, to a gigantic replay buffer, and then train this neural network to estimate the cumulative regret condition on an information set. So it's really just doing MCCFR, but now I'm training a neural network to take in an information set and output the cumulative regret for all of the actions that are at that information set. And they get some good results on poker and are able to beat NFSP. And DREAM reduces variance a little bit with a history value baseline. But the problem with both of these methods, and this is a really big problem, is that the importance sampling term that they inherit from MCCFR causes this estimator to have really high variance, which makes it really difficult to train neural networks in large games. So in particular, in games that have long horizons, you can imagine how this importance sampling term, which is this joint probability of going to this terminal history, is going to get extremely small. So, you know, when I divide by this, it's going to make things have crazy high variance, which is really bad for neural networks. So we would like to get rid of this importance sampling term altogether. And that's what we do with ESCHER. So with ESCHER, you know, we're showing importance sampling in games using a history value function to estimate regret. So what we mean by this is that we're getting rid of importance sampling and replacing it altogether with this history value function. So now our estimator isn't this MCCFR estimator, but it's just going to be a history value function. And for the next couple of slides, let's just assume that we have access to this Oracle history value function. But of course, once we scale it up, this history value function is going to be learned using a neural network. Okay, so we remove this reach weight importance sampling term, number 2, by sampling from a fixed distribution. And I'll talk a little bit more about what that means and why that's important. And I'm going to replace this estimator of the history value with a learn value function. So we're not just estimating this with these rollouts, but if we have this learn value function, we can use that to replace this estimator on the right. Okay. So I know this is a big wall of math, so feel free to you know, skip over this section. But for anyone that's interested, this is a proof that the estimator that we have, which is again just the history value function, right here, is unbiased. So and it's unbiased in a kind of a weird sense. It's unbiased in the sense that it's not fully unbiased. It has this weighting term W of S on top of the counterfactual regret. But that's okay because this weighting term flows through the MCCFR proof, and we're just going to get some additional regret term that you know, goes down to 0. So this is guaranteed to converge. Okay, so going through line by line. So this going from line 1 to line 2, this is the definition of our counterfactual value estimator. Instead of saying all the terminal histories that are in this information set S, I can break this out and say all of my histories in S, and then all of my terminal histories that are descendant of those histories. And then now we can use this insight that the reach weight to get to these histories, if I sum up over all of them, of these histories within H, that's just going to be equal to the probability of getting to H, of my reach weight to get to H. And that works because this Z of S is just H. It's just going to be the H for all of these Z's. Okay, so now this is the important trick, is I'm going to separate out the reach probability of reaching history H in terms of my contribution and in terms of my opponent's contribution. So my contribution actually turns out to be the same for all of the histories in S. And that's by definition of information set, I can't distinguish which history I'm in. So my contribution is just going to be the same for all of them. But of course, my opponents will change depending on the different histories. So if you look at this term here, this is exactly equal to the definition of counterfactual regret, which is what we wanted. So we have this counterfactual regret, but we have this additional term here, W of S. And I changed the notation to say W of S to make it clear that if we sample from a fixed distribution for player I, for me, then this W of S won't change from one iteration to the next, which is really important to make sure that everything flows through in the proof of convergence. So I have this W of S, which is fixed, and again, just flows through, everything converges, and it's unbiased. As long, so like the term that I end up having in my regret bound is just going to be an inverse term of the minimum over all information sets of W of S. So that theory is kind of pointing us towards the fact that we want this W of S to be about the same for every information set. So we should probably use something like a balanced distribution. And that theory also points to, like, for example, if I have a W of S that's 0 for some information set, then my regret can be unbounded because I could be doing, I'm not actually updating that information set, which could be really high regret. Okay, so that was a ton of math. Maybe it was unnecessary, but I think it's cool. So the main takeaway here is that everything works in the tabular setting. So rest assured, things work well. So here's the actual tabular Escher. And again, this is assuming we have an oracle value function. So this is really just kind of for understanding. It's not really something that a practical algorithm, because to get this oracle value function would be way too costly to compute every time. But we're just going to be sampling trajectories using this sampling distribution where player I is fixed to get that constant weighting. And then our regret estimator is just going to be this history value function that we had before. And then just like this is the same thing as in MCCFR, I'm going to update my total estimated regret of action A at info set S. And then I'm going to update my pi via regret matching or some other no regret algorithm on this total estimated regret. And then I return the average policy as before. So the only change with Escher and with MCCFR is that I have a different estimator for my counterfactual regret. But it still works as long as I have this value function. Okay, so I've been kind of alluding to this the whole time. The whole reason we're doing all this algorithm is for scaling up to the deep neural case, in which case we're going to learn some history value function Q on data from pi. So, I run a bunch of trajectories with pi, and then I learn my history value function Q. And you can do this with a lot of RL tricks, which I wasn't able to get around to doing. But this is just a value function from pi. Everything's the same thing as before. But again, I have this different estimator now with my Q given theta. So this is my neural network now. And then I add these to a cumulative regret buffer. And then I train my regret network on the cumulative regret buffer. So everything here is the same as you would find in deep CFR, for example. But the difference is that now I need to train a history value function and use that in my estimate of regret. But everything's also the exact same as deep CFR. Okay, so these are tabular experiments. So I actually compute an oracle value function, and I assume that I have that for free, which I know is not a good assumption, but it's just to illustrate what's going on here. So the exploitability results, nothing interesting is happening here. Everything works, at least everything's converging, it looks like. But what's really interesting is you look at the variance of the regret estimator. So MCCFR, as expected, is extremely high. DREAM improves it somewhat, but it's still orders of magnitude higher than Escher. And these are for pretty short horizon games. So Battleship, Liar's Dice, like they don't have that many actions. So as you might expect, as the horizon of the game gets larger and larger, the variance gets much higher. So this variance of these regret estimators is what we think leads to DREAM failing in these large games. So I have 3 games here. So it's the same game. Each column is the same game. So Phantom Tic-Tac-Toe is tic-tac-toe, except I can't see the other player's moves. Dark Hex 4 is like Hex, which is this perfect information game, except again, I can't see the other player's moves. And Dark Hex 5 is just the same thing, but on a 5x5 board. So as we go from left to right, we get bigger and bigger game sizes. And on the top row, we see the performance of Escher in a head-to-head comparison with NFSP and with DREAM. And in the bottom row, we see a head-to-head comparison with Escher versus random and DREAM versus random, NFSP versus random. So as the game gets bigger, moving from left to right, we see that the relative performance of Escher versus DREAM and NFSP gets better and better. And if we look at the bottom row, as we go into a bigger and bigger game, we see that Escher is always able to beat random, but DREAM and NFSP sort of fail on these types of games. So this is pretty interesting. Okay, so that's all the results I have, all the theory. So some future work, and hopefully we can have a little bit of discussion, talk about this sort of stuff. So a lot of things left to improve Escher. So for example, this sampling distribution that I have seems really unsatisfying to me to sample randomly. So like think about like if I have a game that's like some sort of continuous control type game, you know, I don't want to be updating all these information states. Most of these are going to be really garbage. Like what if I had a game that's like this entire game is all zeros essentially? So I don't need to think about it, but my random sampling will just always stay in this portion of the game. So that's really unsatisfying to me. So how do we think about how to do this optimally? And then of course there's some RL tricks for this value function. So everything that we do in reinforcement learning to get value functions to work can be ported over and should be really helpful. I think it's a big reason why Escher like fails and like doesn't work as well as I would like it in certain cases. Learning this regret network is also a little unsatisfying. I need to keep this big replay buffer of regrets, and then I need to learn the average regret, which can be something that's a little bit difficult to learn. So there's definitely connections here with policy gradient approaches. You can kind of view policy gradient approaches as just updating the policy directly, where my policy is like, hedge or something like this, or multiplicative weights. So I can kind of just view like those policy gradient methods as just directly updating the policy instead of going through estimating the cumulative counterfactual regrets and then building a policy on top of that. So there's interesting connections and interesting ways. I'd love to kind of do some ablations or mixtures of these two approaches. CFR plus is a much faster tabular CFR method where you essentially get rid of the negative regrets every time. But I don't really know how to do this with CFR, with deep CFR. It's kind of an open question how to do that. With general sum and multiplayer games, one solution concept that exists is correlated equilibrium, where there's some sort of one way to think of it is like you have a central mediator that sends actions to every player, and then those players can choose to take the action or not. And a correlated equilibrium is this setting where every player is incentivized to take their action. So it's kind of the only good solution concept we have in general sum games. And I think that if you just, I know that if you just run CFR on general sum games, then you're going to arrive at a coarse correlated equilibrium. So I think you should be able to do Escher in these multiplayer general sum games and arrive at a coarse correlated equilibrium as well, but I haven't fully thought it out. And then last iterative techniques, it would be nice to get rid of this need to have the average policy. Maybe it's, takes up a lot of space storing these neural network checkpoints, or you don't want to train an average policy. So a big benefit of some of these other policy grading approaches is last iterative techniques. So it'd be nice to get some of those as well. Okay, so here's the bibliography, and this is joint work with Gabriele, Mark, and Thomas. So yeah, thanks for sticking with it. I know there's a lot of math, so hopefully it wasn't too daunting, but yeah, thanks for having me.
Just gonna clap silently alone.
Thanks.
Yeah. Thanks for this presentation. Yeah, clap, clap, clap. If we want to turn off the recording for the questions, if that's possible.